Vaccines. So I've tried epidemiology for a while, but when you kind of look at the occurrence of different diseases and infectious diseases, and you see when that vaccine was introduced, the curves look really cool. So you'll see the cases kind of going along over time like this, or maybe even increasing, and then the vaccine's introduced, and that plummets down to almost zero. You can almost tell, like, I don't do this in the final, but if I gave you a graph, and I put like A, B, C, D, and E across like time, and I asked, it's like, oh, where do you think the vaccine was introduced at? It's where it drops and plummets. That does not hold true all the time, but like the vast majority of the time, that holds pretty true. So they are our best defense against different infectious diseases that we actually have vaccines against. What's the best way to combat an infectious disease? Don't get the infectious disease in the first place. And then you don't have to worry about different toxicities, antimicrobials, and things like that, because you never got sick. So those vaccines are going to build a host immune system memory of a particular pathogen. That's needed for the recall response. So remember, we talked about that before. When you have a primary response to a pathogen, you have to have interactions between B cells and helper T cells. When you're exposed to that same antigen the second time during your secondary response, you can also call that a recall response. You don't need that interaction between the B cells and helper T cells. B cells can turn on their own when you open up your B cells and start making antibodies. So the response is more robust and it's quicker too. So vaccines essentially service that first visit to your immune system. Then when you're actually exposed to the real pathogen, your immune system has a memory of seeing that pathogen. So you're breaking the chain of transmission. These vaccines this is really going to date me, but these vaccines have increased life expectancy. Did they ever play Oregon Trail in here?
Yeah.
Oh, you liars, thank you. That made me not feel so old. Maybe I played it on a different computer system. But we would play that on like, I can't remember what the old computers were. They were like old apples, like with the orange. The what? No, it was like black background with like orange font. It's like, you didn't play on that. I don't think those exist anymore. But what do you always die from on Oregon Trail? You get dysentery or something like that. Well, we don't see those things anymore because we have vaccines and we have better water treatment systems. We have all these things that they didn't have back when they were selling the country. The vaccines, one of those things. Recall response, again, faster, stronger, more specific. During your primary immune response, does anybody remember what the first antibody type that's made is? IgM. What's the second one that's made? What about the secondary response? What's the first one that's made? IgG, and then the second one is IgM. So that's because IgG is a lot more specific. So you get a more specific immune response. So you get that. Usually, primary immune response, around a week, maybe a week and a half, you start to see increases of antibodies being made. Secondary immune response, 4 days, maybe, you start to see antibodies spiking up. None of the vaccines that we're going to talk about or that exist are 100% effective. You can still get sick even though you have a vaccine against the different pathogens. But what tends to happen is you're either asymptomatic, you don't know you came across the disease in the first place, or your symptoms are a lot less severe. And this holds true. I think this is probably easier to explain if you think about some of the COVID vaccines. So somebody takes a COVID or SARS-CoV-2 vaccine, and then they still get sick. Well, they may still get sick, but they're not going to get anywhere near as sick as they might have gotten if they didn't have any of the vaccines in the first place. That's all this means. None of the vaccines are really 100% effective. Different vaccines, some have been along for a long time. Jenner, back in the late 1700s, started to realize that milkmaids that actually milk cows would get the disease from cowpox. It was kind of like smallpox, but less severe. And those people that are exposed to cowpox and had a cowpox infection were not susceptible to getting a smallpox infection. Why is that? Those two viruses are related to one another, so there is some similarity. So if you vaccinate somebody with cowpox, they'll become immune to smallpox. So we've known about that for a long time. Pasteur in the late 1800s with the vaccine, came up with the first rabies vaccine. So we know a lot of that. Walter Reed, which is where they do Army infectious disease research. They still do research out there, Walter Reed, on this kind of stuff. They developed the first yellow fever vaccine, and they also developed a lot of the initial influenza vaccines. So there's a lot of different vaccines that some of these institutions have been comparatively making. Different kinds of diseases you've seen over time. Diphtheria used to be about 200,000 cases with about 15,000 deaths in the 1920s. Tetanus, before the toxoid vaccine, you see a lot more cases of tetanus. Remember what a toxoid vaccine is? What's a toxoid vaccine? We'll talk about this maybe a little bit today. Yeah, it's just a toxin. So you take the toxin, you inactivate it, it's usually chemical deactivation or inactivation, just say chemical inactivation or heat inactivation, and then you take that inactivated toxin and you inject somebody with it. And then your body will make antibodies, it's technically antitoxin, to the toxin. So those two, you can get sick. You could still get a infection from that, but a lot of the ones that use toxoid vaccines, those pathogens, the toxin is the thing that makes them pathogenic. That's the virulence factor. So if you have immunity to that toxin, bacteria doesn't really do anything. That's like its main weapon. So you block that, you're good. Polio, about 20,000 to 300, or 20,000 to 30,000 paralytic cases in the United States today. That's gone. Will that increase again? I hope not, but I think that's going to, as we have more people not taking some of the vaccines, some of the vaccine hesitancy, you might see cases like that go up again. I think I've talked about this before, but as of a couple years ago, the only places on the face of the planet that had cases of polio were Afghanistan, Pakistan, and Nigeria. The Nigerian government had a very active vaccination campaign against polio, and they got it down to like 12 to 15 cases a year. Those are from the oral polio vaccine because that vaccine is attenuated. So those 12 to 15 cases were people getting polio from the vaccine, unfortunately. They use that in Nigeria because it's a lot cheaper and it doesn't need cold storage. It's in sugar cubes, so it's easier to transport around. Afghanistan, Pakistan, you have different kinds of conflicts going on there. In the terrain in those countries is extremely mountainous and remote. In some of those places, so it's very hard to get things in those regions. But as of now, those are where you see the most cases of those countries. All kinds of things can be vaccinated, obviously us, regardless of age, and also different kinds of animals. You know, if you have any kind of pets, you go in, you get vaccinated for different things. Even wild animals can be vaccinated. I think I might have talked about this a little bit before with rabies. If you have a population in, say, like a national park or something, and you realize there's a population of rabies that have become a population of raccoons that have been infected with rabies, you can throw out these little like treats. The treats have the vaccine for rabies in it. The raccoons eat up the vaccine. The ones that do not have rabies or have like early rabies, they'll be essentially immune from that disease process, and the ones that are too far gone will eventually just succumb to the disease. So you can eradicate it that way. Then you don't become exposed to rabies through the fallen animals. We talked about herd immunity a little bit before, so that's the percent of the population you have to make sure that is immune to protect the people that cannot get the vaccine, that are not immune to the disease process. And depending on the pathogen, specifically, one of the main things is it's R naught. The higher that R naught, the higher that herd immunity has to be. Does that make sense? So the easier it is to transmit, the more people you have to get immune to it to protect the people that can't get vaccinated. That's essentially what herd immunity is. The lowest you can go, 80 is kind of a stretch. The lowest you usually go with herd immunity to protect the entire population. The low end's around 85% usually. Maybe as low as 80 in for some handful of pathogens, but most you're going to have 85% and above to actually protect the people who can't get vaccinated. All right. We talked about all this. The vaccinations themselves are really hard to actually make 100% effective. There's a lot of reasons for that. So some of the pathogens you're going to have minor differences. Influenza is actually a good example of this. This is why we have to get vaccinated for influenza every year. You have one little point mutation, the vaccines against, like, say, spike proteins on surface influenza virus like hemagglutinin. You have a point mutation in that hemagglutinin, that vaccine is worthless. Same thing holds true for some different bacteriological pathogens. I'll give you an example of one of the organisms I work with. There's been some good studies that were done by some of my colleagues, where they'll look at, like, vaccine that targets capsule on one of these bacterial pathogens. Well, not all the bacterial pathogens in that group make the same kind of capsule. About 70% of them do. If you're unlucky enough to get one of those other ones, 30% that doesn't make that kind of capsule, that vaccine is completely worthless. So trying to find a vaccine that actually gets everything, like all this strep pyogenes that cause strep throat, or all the Acinetobacters, or all of that, that's a tall order. There's just so much variation between some of these different bacteria. Again, we talked about this a little bit too. Immunity declines over time. There's a couple different reasons for that. One of the reasons is you get older, unfortunately, your immune system starts to get weaker. And as your immune system gets weaker, you might not have as good of an immune response anymore. So that's for things like if you had chickenpox with the chickenpox vaccine when you were a little kid, you might end up taking a booster called Shingrix when you get about 55 years old, because your immunity to that pathogen starts to wane. So you have to stimulate your immune response again. The way you do that is by giving a booster. That Shingrix vaccine is exactly the same as the chickenpox vaccine. It's just like a 7 times dosage of that chickenpox vaccine. So it's just a lot higher dosage. So that stimulates your immune response, so it starts recognizing again. So if you are unlucky enough to actually have that virus come out of your dorsal root ganglion, hopefully your immune system stops it before it gets too bad. Okay, so one of the main things I want you to be familiar with is the different kinds of vaccines. So, and the different kinds of immunity, which we've talked about some of these already too. So active vaccines are going to carry some kind of a modified form of a pathogen. It can be weakened. We talk about a weakened pathogen. It's referred to as attenuation. We've talked about that in here too. A lot of the stuff we're talking about today is actually things we've already talked about. If it's attenuated, you can do that a couple different ways. You can throw it up in the lab. You can genetically mutate it, where you weaken it through genetics. Like say you have a strain and you take out the variant factors, take out the genes. There's different ways you can go about weakening it. So active vaccine is going to have some form of that pathogen. Designed to prevent infection or serious disease, long-term protection due to immune memory is important for those kind of vaccines. And then you have the passive vaccines. So those are neutralizing antibodies. Examples of this: if somebody gets a snake bite, you give them passive immunization with antibodies, antitoxin against those toxins. So active versus a passive vaccine / immune response. So we talked about those already. When you talk about natural passive immunity, so naturally you usually get antibodies from your mother, so that can be in a couple different spots. So you can have that getting IgG in utero through the placenta. IgG is the only antibody that crosses the placenta. The other antibody you can get from your mother as a natural passive immunization is in breast milk. That's IgA. And that protects you for a while. Those antibodies do have half-lives, so they last months, and eventually they degrade. And since you have not been exposed to whatever those pathogens those antibodies recognize, you will be susceptible to those different infections that your mother was exposed to previously. You find the most antibody in colostrum, which is the early breast milk that's produced. You can see the difference in what that looks like. Colostrum looks more brown over in the bottom left versus after initial breast milk was produced, which looks more like regular milk, more white. That colostrum contains a ton of IgA. So that's a good natural passive immunization. Another passive immunization, and we talked about this a little bit, but not specifically in this context. So you can use passive immunization using antibodies against different toxins. As soon as you have those antibodies, they'll block or inactivate the activity of the toxin, but you're not going to have an immune response against it because your body did not make those antibodies. So the classic example of this kind of passive immunization would be where the Iditarod snow dog race came from. So that was actually to carry anti-serum against the diphtheria toxin. There's a bunch of people, I can't remember how many. I'm trying to remember how many people in that town were actually exposed to diphtheria toxin. There's a bunch of people in Nome, Alaska that were exposed to diphtheria, and they needed the antitoxin against the diphtheria toxin. You remember what I told you about Corynebacterium diphtheria? Without the diphtheria toxin, does it do a lot? Diphtheria toxin is pretty much the only thing Corynebacterium diphtheria makes it cause the disease process. You may remember where that bacterium gets that toxin from. Bacteriophage, so it's a phage toxin. So if you come across it's called phage conversion. So if you would hypothetically come across the Corynebacterium diphtheria, isolate, they've never been infected with that bacteriophage, I'm not going to do anything. Because that diphtheria toxin is about the only thing that actually makes it diphtheria. So with that said, if you have people with Corynebacterium diphtheria, and you give them an antitoxin against the diphtheria toxin, it takes care of the disease process. So they knew that back in the 20s, and the only way they could get the anti-serum to those people in Nome, Alaska was by dog sled in the 20s. So that's where that dog sled race came from, was get the diphtheria toxin. They started doing it annually after that. That initial antibody that was used to treat diphtheria was actually a horse antibody. So let me explain that to you. If you look down here, so red would indicate you have antibody pieces apart from a mouse, and blue in this little setup here is indicating it's human antibody. So really all you want to block the effect of, like, say, a toxin is up here where your antigens are recognized in this variable region at the top of the line. You want those to recognize the toxin, but as much else of that antibody you want to be as human as possible. Because what happens is if you take an antibody from a chicken or a horse or a cow or a rat or whatever that's against, like, say, diphtheria toxin, and you inject it into your body, it will bind onto those toxins and activate it, but those antibodies won't last a long period of time. So their half-life is going to be very short because those are foreign proteins. Those are foreign glycoproteins. Your immune system is going to attack those antibodies. It is going to degrade them because they're foreign. So what you can do genetically is you can take the genes involved in making the antibody, keep the portion that recognizes whatever you're trying to get to recognize, in this case diphtheria toxin, from the mouse, and replace the rest of the genes with genes that code human antibody. So it keeps as much of the antibody human as possible, except right up here where it's actually recognizing the toxin. So these antibodies that look like this are going to have a much longer half-life than an antibody that looks like this, that's fully from another species. Does that make sense? So you can do that genetically in things like mice. You can make things called hybridomas too, where essentially you take cells, say out of the bone marrow of mice, and then you can genetically manipulate them in cell culture, you can immortalize them, and you can use cell culture to just make antibodies over and over and over and over and over again. You can do it without actually using an animal long term. To be licensed, vaccine must be known to produce protective antibodies and also T cell responses, so you want it to actually activate acquired immunity as well as humoral immunity. That's called correlates of protection. Vaccinated individual must be protected against the disease caused by the virulent form of the pathogen. That's why you usually run trials with these different kinds of vaccines. You develop a vaccine for a disease process that is occurring in the population, and then you do field trials where you take the vaccine and you introduce it in the patient population where they're actually seeing that disease process occurring, and you see how well it does. So those are late stage FDA trials. We kind of skipped some of that stuff with COVID because we were so desperate to get a vaccine out, they did the emergency use authorizations. But usually it takes a long time to get different vaccines and drugs to market. Some of these things take a decade to get through all the FDA trials. A lot of them, and there's a lot of examples, especially for some of the COVID vaccines through here tonight in this lecture, a lot of them never even made it all the way to market, or they've been discontinued, so they don't last that long. For a vaccine to actually go to market, it has to be safe, obviously. You don't want to cause the disease process. The main problem with this is the best vaccines are attenuated pathogens. So if you have a pathogen that is attenuated, that is the same, a very similar form of that pathogen that you're introducing into your body. So it's about as close as you can get to the virulent form of that pathogen without being the virulent form of that pathogen. So it's going to look very similar to your immune system. Also, what happens is when you inject that into your body, it is still a pathogen. So it will, if it's a virus, it's going to replicate. If it's, say, a bacterium, it's going to go through binary fission. Say you inject somebody with 10 bacterial cells that are attenuated. Those 10 bacterial cells are going to become 100,000, 10,000. After you inject that initial dose, they're going to continue. It's like an internal booster. So whatever you inject is going to keep on growing. If you do something like an inactivated vaccine, or it's an activated virus or a bacterium or whatever you inject that person with, that's what they got. So usually for those kind of vaccines that aren't kind of, the pathogen is reproducing on its own, those ones are going to need boosters. The attenuated vaccines usually do not need a booster because they kind of boost themselves. So we'll talk about that here in a little bit. Has to have minimal side effects before it can go to market, obviously. Induces a lasting herd immunity in the population because you want it to actually protect people that can't be vaccinated in addition to the ones that are being vaccinated. You want it to have a low cost. This is a hard threshold to kind of get over. Usually for a vaccine to be really successful, each dose has to be less than about $1. That's incredibly difficult. It's a vaccine that needs cold storage and is unstable and you can't transport it easily, and that's kind of a hard hill to climb too. With that in mind, storage considerations, the ones that can be stored at room temp are a lot easier to maintain a price point that's cheaper. In the delivery as well. Oral is a lot easier to administer. That's why the Nigerians use the polio vaccine in sugar cubes, because it's a lot easier to have somebody eat those sugar cubes than to try to jab everybody. I mean, just think about how much the needle and the syringe cost, or how much space that takes up trying to fly 5 million syringes somewhere. I mean, it's not easy necessarily. What also happens sometimes, especially if you're in an area that's resource limited, you start to see reuse of needles. One person gets a polio vaccine, same needles reused for the next person, for the next person, for the next person. If you're in an area where you have other disease processes that are bloodborne, so yeah, you vaccinated everybody against polio, you gave everybody HIV. I mean, I'm trying to be a little bit funny, but that's kind of what happens. We've seen that a lot in different parts of Africa. So it's like, okay, so you vaccinated against this, but you reuse the same needle for 100 people in a population where HIV is very prevalent, and now there's a lot of people that have HIV, so you're introducing a new problem. That has been a huge problem with different kinds of vaccines that involve needle sticks. Okay, so the different types of vaccines. Live attenuated, inactivated kill, subunit toxoid, RNA, and vector based. So let's kind of walk through these. You do not need to know these specific examples of these vaccines. Some of these vaccines don't even exist anymore. Like this CoronaVac, that was never even licensed in the United States, and by the time it was looking like it might have got licensed in the United States, it was discontinued. So some of these don't even exist anymore. They're just to articulate an example. So there was a Codagenix Biotech had a vaccine. It was an attenuated intranasal COVID-19 vaccine, so it had a weakened form of SARS-CoV-2. Sometimes they refer to that as COVAVAC. Vaccine had a live attenuated strain of SARS-CoV-2. SARS-CoV-2 causes COVID-19. It can still replicate. This one's stuck in late clinical trials. Probably never going to get out of them, to be real honest with you. I think it's still in clinical, like phase 3 clinical trials. clinical trials for FDA only go to phase 4, and phase 4 is when you're actually testing on the population. It's essentially you're looking at the effects after it's already been released. It's never made its way to 4, and if it ain't made it there yet, it probably is not going to. So I would say that one's probably not going anywhere. But that's using a weakened form of that virus. There's another one down there at the bottom that used an activated SARS-CoV-2. It was called Coronavac. That one is dead in the water. But the main thing that I want to show you here is the difference between, again, the attenuated versus inactivated. Give somebody something that's weakened, it's going to make more of itself in your body. If you give somebody something that's inactivated, it's inactivated. It's not going to do anything. So whatever you stick them with is what they're going to get. So usually the ones that are inactivated, you have to give them a bunch of boosters because they're not replicating themselves. Again, attenuated vaccines are made from weakened microbes. You're going to need booster shots for the inactivated, but not for the attenuated, most likely. And the closest thing to actually a natural kind of infection you're going to get is an attenuated vaccine. The inactivated vaccines, again, they're going to be an activated virus, a pathogen, whatever we're talking about, the pathogen being heat chemicals are used to inactivate those pathogens. But again, they're not infectious. Whatever you inject them with is whatever you inject them with. You're probably going to have to give a bunch of boosters. And I've talked about this in here before. This is the vaccine for polio we used to give in the United States. This is the vaccine we give for polio in the United States now. This one could give you polio. This one could not give you polio because it's inactivated. Makes sense, right? I think I've even talked to, this lecture was a lot of repeats. I think I even talked about this in here too. So the way we do the influenza vaccines is every year before flu season, we see what the prevalent strains of influenza viruses are in the southern hemisphere. We use that to predict what we're going to see out here in the northern hemisphere. Sometimes that is a good predictor, sometimes that is a terrible predictor. That's why sometimes the efficacy of the vaccine is like 80% and sometimes it's 40%. Sometimes we just don't see the same thing that they saw in the southern hemisphere. And then in return, the southern hemisphere before their flu season sees what the prevalent strains were in the northern hemisphere and they use that to produce their influenza vaccines. And sometimes that bites them in the butt too. It just doesn't work all the time. But that's kind of how we do the vaccines, for influenza virus at least. Unlike a lot of the other vaccines that take a long time to go to production, they've kind of got this one down to a good process now to where it can move real fast because the FDA knows it's coming every year. They know the process by which they pick which strains they're putting in it. They share that information with the FDA and they make the thing. Pharmaceutical companies have contracts to make these, federally funded. They can move real fast on those. There's been a lot of debate over the years if this is eventually what's going to happen with SARS-CoV-2 vaccine too. Essentially that thing mutates all the time. So is there a point in time where maybe they can have like a joint, like SARS-CoV-2 influenza vaccine? Those are different types of vaccines. It's going to be a while probably. But that has been the thought process by a lot of my colleagues over the past few years. It's like, maybe this is something that should be thought about to be a seasonal thing. Because it mutates so often, that would be a good time to do it. But that's kind of hard to figure out because we're still learning about mRNA vaccines by the day, unfortunately. We don't know as much about those as what we probably should. So then you have subunit vaccines, which is exactly what they sound like. They take some component of whatever the pathogen is, and you inject them with that. Maybe it's a part of the capsule, maybe it's some kind of a virulence factor secretes, some protein on the surface, and then you use that subunit of the whole pathogen and use that to vaccinate against. Those are going to need boosters, because whatever, if you inject them with some kind of virulence factor, some protein, how much of a protein you inject them with, it's not going to make more protein, so you need boosters because they don't replicate. Take the vaccine, let's say you're using a bacterial cell, take the bacterial cell, break it apart, centrifuge it, get different pieces apart, you can purify different proteins, and you can take the genes, say if you're trying to, let's say you're using some molecules for some kind of a bacterium. You take the gene from that molassen, grow it up in E. coli, have the E. coli make a bunch of it, purify it, and activate it, inject the people with that. So it's just a subunit. An example of this is the acellular component. Sometimes you see that abbreviated AC for the pertussis vaccine. They use components of Bordetella pertussis to vaccinate against pertussis. For pertussis, those components they use are parts of the capsule, because that's what's on the outside of Bordetella. That's what your immune system's going to see. Again, we talked about this a little bit too. Problem with that, your immune system created about recognizing proteins, really sucky at recognizing sugars. That's what the capsule gets out of those polysaccharides. So the immunity to this acellular component of this pertussis vaccine is going to do something called wane, and over time, between about 5 to 7 years, you're probably not going to be immune to it anymore. That's why you have to get that Tdap or Tdap as a booster.
Like every 10 years.
They say 10. They say 10 more for tetanus, even if tetanus is longer living, probably than the 10 years. But what we've seen over the past decade or so is for pertussis, you don't have a lot of immunity to pertussis in 10 years. Some people make it to about 7. Some people I make it to about 5. My wife, my brother-in-law, and all the people I know have had that pertussis vaccine in less than 7 years, and they still get over cough. It's a crappy vaccine, but it's all we got. I mean, that's just kind of the nature of that pathogen. That's what's on the outside of it. That's what your system sees. And there's not really anything else sticking out through that capsule to vaccinate against. If you say you take something that's underneath that capsule and use that in a vaccine, it's not going to do anything because your body's not seeing that. So we're kind of, some of these ones that make capsules, we get a little stuck on. Pertussis is one of them. We do a vaccine, which is very not any vaccine, but it's not the greatest vaccine. You can make these components of the subunit vaccines. Say you're trying to grow up some kind of a protein again, you can use bacteria or yeast cells or what have you to make more of that protein, purify it, use and activate it, use that in the vaccine. You can also take insect cells, grow them up in cell culture, and use them to produce those proteins, a bunch of them. Insect cells make more, essentially have a higher yield than what you would see out of using bacterial cells for protein purification. So you can use insect cell culture. Same kind of process though. Overexpress the gene, makes more of the protein, and then purify the protein and activate it, inject it. Some different vaccines you can see there. They're made using that mechanism. You do not need to know this process. I essentially just explained it to you that you don't need to know that. A special kind of subunit vaccine is called a toxoid vaccine. And that's when the subunit that you're purifying and then activating to inject into somebody is a toxin. That's it. So toxoids inactivated toxin. So technically a toxoid vaccine is a subunit vaccine. It's just that subunit is the toxin. Microbes culture and rust, secrete the toxin, purify the toxin, activate the toxin using heat or chemicals. Again, just like a lot of these other ones we talked about, once you inject that toxin, that activated toxin into somebody, it's not going to make more toxin, you're going to have to get booster shots. Like we were talking about with the tetanus vaccine, the tetanus component of the tetanus vaccine is a toxoid. So you have to stick people once. That is another reason why, even if it's been less than 10 years, if you step on a nail or something that we think might introduce Clostridium tetani into your system, that you get a booster shot, because better safe than sorry. Obviously, you don't want tetanus, so you might have had the tetanus vaccine last year. They're probably still going to give you another tetanus vaccine if you step on a nail or something, because the chances are you're getting exposed to it's higher. So, the hepatitis B vaccine is a subunit vaccine. Technically, the hepatitis B vaccine is not just like one little protein or something from the hepatitis B virus. What it is the entire capsid from the hepatitis B virus. It just doesn't have any genetic material inside. So it's an empty vector, is what's referred to. So it's an empty viral particle. That's a really good way to stimulate an immune response, because that's what your immune system can see. Again, though, that is a subunit vaccine, so you might require booster shots for that, because there's no replicating after you inject it. The hepatitis B vaccine is considered one of the cancer vaccines. Different hepatitis viruses can lead to different kinds of cancers, so being protected against the hepatitis B virus protects you from getting different kinds of cancers like liver cancer. So it's considered a cancer vaccine. Same thing for human papillomavirus. Human papillomavirus, we talked a little bit about, there's some different strains of human papillomavirus associated with different kinds of cancers, colorectal cancer, oral cancer, penile cancer. If you're protected against those strains, a vaccine like Gardasil, the chances of you getting those kinds of cancers is significantly decreased than if you weren't vaccinated against them. So that is also considered a cancer vaccine. Obviously, it's not vaccinating against cancer, that's not a thing, but it decreases the likelihood of you getting those different kinds of cancers. Yeast or mammalian cells make empty papillomavirus particles, just like the hepatitis B vaccine. So you have the whole virus, but it doesn't have any genetic material inside of it. So it's just an empty shell. You can use yeast cells or insect cells to generate these empty virus particles. Did I talk about how viruses can have assembled when we talked about viruses? Probably not. So if you take the genes for the proteins that are used to make a virus particle, the capsid, you can express those in an insect cell line, a yeast cell line, whatever, it doesn't matter. Those cells don't have to have any additional genes involved in like assembly of those viruses. Those capsimeters, like little pieces of parts of the capsid, the lowest free energy state for those that exist is when they're assembled. So if you have just a hodgepodge of different pieces of parts of a virus, they'll self-assemble. There's not any other genes or anything involved in like putting those pieces together. They do that on their own. For those of you that had chemistry recently, it's essentially the lowest free like energy state is for those that exist as a virus particle. So that's how you can put these. That's probably worth explaining. That's how you can put like these genes, these proteins, in something that's not related to like us at all, and they'll actually assemble the virus. Gardasil 9 has 9 different virus-like particles, so sometimes these empty virus particles you see referred to as virus-like particles. They can be produced in yeast for that reason. They just assemble on their own. And then you can have nucleic acid vaccines, mRNA vaccines. So a lot of the SARS-CoV-2 vaccines are mRNA vaccines. We've done a lot of work on those over the years. There's still a lot of things to figure out about those. There's really only a few that are on the market, at least mass capacity. Some of the SARS-CoV-2 vaccines, as well as the recent RSV vaccine is an mRNA vaccine. Essentially what happens is you take mRNA that codes for like a spike protein on one of these viruses, and you encase that in a liposome. So like a little lipid particle. That little lipid particle that has mRNA inside of it is going to go to your cell. The membranes are going to fuse, and it's going to release that mRNA into your cell where protein will be made. That spike protein will be transported to the surface of your cell, and then your immune system can recognize it. There's a lot of research that's been done on mRNA vaccines. There's also a lot of research that's not been done on those because one of the main investigators for this stuff is big, not even big anymore, has begged NIH for probably 30 years to fund his research more, and they never really gave him a lot of money until the COVID-19 pandemic hit. And I think then they pretty much backed up like a dump truck full of money to him. So he was very underfunded until all this happened, because he's been screaming that was going to be an epidemic long before it was an epidemic. So they kind of funded the party a little too late. So some of those investigators weren't the greatest funded, so they're kind of playing catch up, trying to figure out how some of these work. What else is important about that? That's probably the main part. This is essentially what I just explained to you, how it gets in. And then you have some other kinds of nucleic acid vaccines. So these are actually DNA vaccines involved in the introduction of appropriate tissues. Again, they're lipid encased like the mRNA vaccines, but these little lipid encased plasmids carry DNA sequences instead of mRNA. They get into the cell, they get into your cell, DNA is converted to mRNA, mRNA into protein, protein goes on the surface, essentially the same thing, except the DNA is going to the cell instead of mRNA. Usually the genes, like say for a spike protein, for these kinds of nucleic acid vaccines are included on a plasmid. Plasmid ends up existing as a plasmid inside your nucleus, which you usually don't carry plasmids, but if they're put together correctly, you can carry them long term. DNA vaccines, cell won't tolerate DNA in the cytoplasm, so DNA vaccines are designed to enter into the nucleus. The DNA exists there as a plasmid again, and then it can be converted into mRNA, and then mRNA, protein to the outside of your cell. And then you can have viral vectors, which we kind of talked about this, but not in this context. So we talked about this more in the context of gene therapy. Essentially, remember how I told you you can use different viruses like adenovirus. If you have somebody that has like a defective copy of the gene, you can put the non-defective copy of the gene in with the virus affects them, they get exposed to that good copy, and they can swap in with the good copy. You can do the same thing for a vaccine. On that virus, you have a sequence for SARS-CoV-2 spike protein. When that virus infects your cells will make that spike protein goes outside your cell, immune system makes the spike protein. So it's using the same process. Instead of trying to replace a defective gene, you're trying to introduce a gene or something under the pathogen. And we talked about this a little bit too. So the problem with the different vaccines is a lot of it is with storage. So you've got to figure out different ways. A lot of vaccines, this is a problem with a lot of the SARS-CoV-2 vaccines as well. A lot of those require deep storage, like deep freezers, -80 or even lower temperature than that. For those of you that have been around here doing research, you see a -80, not an easy thing to kind of throw in your pocket and walk around with. It is a big, heavy freezer that's on wheels, and even though it's on wheels, it's still very heavy and hard to push. So it's not something you can transport around typically. If it's one of the vaccines that requires even deeper cold storage than that, like say it requires being stored with nitrogen, then you got to figure out a way to try to get a liquid nitrogen viewer all over the hillside. It's hard to transport those things. The harder it is to transport, the more money it costs. The more money it costs, the less chances you're going to get it's going to be distributed widely. Yeah.
Your research on this here, you make like nucleotide solids to transport vaccines to emergency.
Cool. Yeah, there's some people that do research on this stuff. They've had different successes with storing it with like different vaccines. You can store the pathogens or the subunits or whatever on like silk. They do better. They have these microneedle things which they tend to store better. I mean, there's a lot of people doing research on this stuff, trying to figure out how to not have this cold storage everything because, I mean, truth be told, those freezers aren't cheap either. Buying liquid nitrogen is not cheap. Like none of this stuff is cheap. And also, we ran into the problem with this during like the pandemic. We didn't know where to put the freezers because we literally ran out of space. The same thing kind of held true if, remember for a while we were taking plasma from people that survived like a SARS-CoV-2 infection. We were using that to like massively immunize people that had an active infection. And some of those trials showed some promise and some of them didn't. But we didn't have any place to put plasma for a while. It's like, okay, great. If you have all these people wanting to donate plasma, that's great. Where are you putting the plasma? Because if you have nowhere to put it, so it turns into a bit of a pickle, especially with that situation because you're trying to have different cold storage for vaccines, but then you're also trying to have different cold storage for the plasma. And eventually, I mean, like we couldn't walk down the hallway. Like I had to go like this, like move -80s to get down to the lab. of situation again. One can do. So there's different things, even mixing different sugars with some of the viruses that are used in vaccines are shown to allow them to be stored longer. So there's a lot of research with this. You can use different adjuvants. So adjuvants are these non-specific things. Sometimes there are components of plants that stimulate an immune response. So if you want to get a really robust immune response, you mix, say, your inactivated virus with an adjuvant, and that will stimulate your immune response to have a better response against whatever you're injecting people with. So example of this is I would use something called Froom's adjuvant. So if I was trying to make antibodies against a protein, I would mix up my protein with this adjuvant. You mix it up. I never bring this. All kinds of little displays I never bring. There's like this little valve. You can have a syringe over here with adjuvant and a syringe over here with your purified protein. And then you have this little valve that goes between the two, and you literally go like this and just pump them back and forth to get them mixed up. And then you take that emulsion, and then you can inject that into a rabbit, and then they'll make more antibodies, more specific antibodies to whatever that protein was, than if you just inject them with the protein by itself. With the adjuvant self-stimulated and immunological. Never brings the demos in here. I'm the worst. Sorry. So you get a better response with those. You do not need to know all these, but just make sure you're familiar with the different types of vaccines. I feel like that went really fast because I feel like we've talked about 80% of this. Does that all make sense? The different kinds of vaccines, kind of be familiar with how they work. You do not need to know the different examples of like, give me an example of a subunit vaccine. You're not going to do it. But know what a subunit vaccine is. Yeah, what's up?